Thank you for joining me this morning. My name is Daniel Lazier. I'm a product marketing manager at Markforged. I've spent time in a couple different parts of the business at Markforged here. Got started as an application engineer. Met probably a few of you out there in the field, just sort of working on parts designs and processes with our printers. And today I'm super excited to talk about the introduction of our newest material, Precise PLA, which is really devoted to helping you bring the complete product lifecycle to life on the Markforged digital forge platform. So just to get started, and again, I won't dwell on this too long, but really at Markforged, what we're about is tailoring every element of your experience as a user at every surface of our platform so that you get great parts out every time. So that starts with our software. When you upload your part, slice it, and set it up for success. We've spent a bunch of time and effort to curate and cultivate an experience that's really seamless, simple, and easy for you to use, where you kind of get the highest ratio of limited user input to great parts out with a bunch of great capabilities. I'll talk a little bit about the materials and the hardware in a second here. The printers themselves are purpose-built to print really, really great quality every time. So if you've taken a look at our website, you've probably seen all the little details that go into making these printers super robust and accurate. I call attention to the unibody chassis of solid hung of aluminum under the hood of the printer that helps to resist sort of the micro torques that arise from the belt drive system. And we've got 9 printers across the fleet that are really sort of purpose built to address different stages of the product lifecycle and different applications. We'll talk a lot about applications in the context of this call today. With the introduction of Precise PLA, we've now got 23 unique and proprietary materials that I think that if I were to take one point from this slide, it's that each of these elements, software printers materials are all tightly integrated so that the interfaces between the two really feel like one unified experience. And this really results in a great end user output that really sort of manifests itself in the quality of the parts that I get every time out of the printer. Just to shine a spotlight on the hardware itself, you can see if you're looking at my camera screen here, you can see I'm lucky enough to have 3 of these machines in my home here. I've got the industrial series over my right shoulder here. I got the desktop series. I'd like you to meet Laura at the top there. This is Sherman down below. Over my right here, this is Big Mike. So we got a happy little family here in my home office in San Diego, California. So the desktop series is our most mature platform of all of these. So we introduced it in 2016. Actually, our first generation we launched back in 2014, but this latest iteration of it came out in 2016. And it's really devoted to professional use cases, but it's simple enough to go right on your desk. I contend this is the most powerful manufacturing equipment you can fit on your desk. And it takes about the power of 1.5 light bulbs to run it, which is pretty crazy when you think about the kind of use cases and applications you can address with that piece of equipment. The industrial series is sort of the broader extension of that platform, purpose-built to address more nuanced applications where I might need flame retardant materials or ESD safe materials. The really cool thing about the industrial series is that it brings in a layer of automation and accuracy by way of, it's actually equipped with a laser on board. That laser not only does calibration at the front end of your print process, it can also do inspection and some automated quality control on board that machine. The Metal-X system, which is inclusive of both this Metal-X printer and this sintering furnace, is purpose-built to print great quality, highly efficient metal parts. And I'll share a little bit about the materials in a second here. Cool. So moving along, and by the way, a lot as we as we progress through this conversation, I both invite and welcome questions. So there's 2 ways to do that. There's the chat box and there's a Q&A option for you as well. And I like to have those questions rolling in and address them as they come in. So far, looks like everyone's sort of providing salutations and providing a little information where they're calling in from. That's great too, but certainly want to address questions while we're here live. Cool. So a little bit about the materials. And this is one of the things that really differentiates the Markforged solution from really anything else that you see out there. Um, so the primary innovation that sort of sparked the growth at Markforged uh, is this top left here, the continuous fibers. We invented a process whereby we lay down a layer of plastic, and then we fuse in a continuous fiber into that plastic, and the resulting body has properties that you'd probably associate more with like a machined or formed metal. So I can really start to address some applications that go beyond just my typical prototyping plastics. We do have a pretty impressive range of plastics themselves. So Onyx is a material that we invented. Onyx is a nylon that itself is doped with chopped carbon fiber particles. Those chopped carbon fiber particles do a couple cool things to the part. So one, it makes it stronger, boosts the strength by about 40%. The second thing it does is it actually makes it a lot more stable from a print process standpoint. The chopped carbon fiber causes the nylon to have a lower coefficient of thermal expansion, meaning you're going to get less warping, peeling. Some of the old suspects from the early days of 3D printing with ABS and PLA that make it a little bit more frustrating to use. I mentioned we also have a couple of specialty flavors of Onyx. So we have Onyx FR mainly for aerospace applications. It can be certified for flight because of its flame resistance. And then we have an ESD safe variant of Onyx, which is really good for electronics manufacturing. And then most recently, and likely the reason you all are here is because we recently announced Precise PLA, which I'd say isn't necessarily changing any kind of mechanical properties of the system or technical properties of the system. What it's really doing is reducing the cost that it would take to get a great part out of the Digital Forge platform, so that I can start to address some lower grade applications that don't necessarily need all these great technical properties. But I'm still kind of looking for that great quality, and in a bunch of different colors. I'll briefly mention, so the metals, less of a focus of today's conversation, but we started off by when we released the system with 17-4 stainless steel, which is great for sort of generalist high strength prototyping applications. And then from there we went into some specialty tool steels, including H13 tool steel, D2, A2 tool steel. And then we have some specialty alloys as well. So we have Inconel 625, which is great for temperature resistance and chemical resistance. And then our most recent addition to this library is copper, which of course is great for both electrical and thermal conductivity. So let's talk a little bit more about this Precise PLA. What is it? What makes it precise? What colors can I use it for? Just some of the basics here. So Precise PLA comes in 8 different colors. So we got gray, blue, green, red, orange, yellow, white, and black, which is a pretty comprehensive library. I've been having a blast printing with it myself. One of the things, it's not complete yet, but downloaded this excavator design, which I'm printing for my nephew. I'm seeing him this weekend. So I've been having a lot of fun with it, and the quality's been great. What makes it Precise PLA? What makes it different from other PLA? Really, the secret sauce, if I were to point to any one thing, is again this tight integration between the materials, the printers, and the software. So the team put just an insane amount of time into testing a bunch of different geometries across a bunch of different print profiles, and sort of purpose tuning the system to print our precise version of PLA with incredible accuracy and repeatability. So when I put that material into the printer, I know it's gonna have a great part out every time. A little bit about the platform itself. So the print systems themselves, I sort of talked about the series at a high level. The desktop series itself actually consists of 3 different printers. So here's what that looks like. So at the low end, we have the Onyx One. That's our lowest cost offering. That's just shy of $5,000. And the Onyx One, it just prints Onyx. I like to think of it kind of like the In-N-Out hamburger, which we have here on the West Coast of the United States. They really just do one thing, and they do it super well with great repeatability. And that's really what makes that print system great. People love this printer because of its simplicity and just the consistency with which it prints that material. The Onyx Pro, which is our next sort of offering up this line, which is around $9,600 US. That print system does Onyx with Precise PLA. So that's the first one that sort of introduces these materials devoted to concept modeling. And it also brings to the table the continuous fiberglass material, which is really great for like moderate loads. So I would think of like tools, fixtures, robot grippers, all those pretty solid applications for continuous fiberglass. The Mark II is our top of the line printer here. That's about $20,000 US. So that's gonna bring into the platform, incremental to the Onyx Pro, a different plastic which we call nylon white. It's just sort of a general nylon. Really where people use that is like bushings, bearing surfaces, things that need low surface friction. And then I'm adding a couple incremental continuous fibers here too. I'm bringing in carbon fiber, I'm bringing in continuous Kevlar, and then beyond just the base fiberglass, I actually have a fiberglass devoted to high strength and high temperature applications. That's specifically really great for if I need to make prototype injection mold tools, or potentially like welding fixtures or other things that are going to be exposed to a lot of heat. So really like to kind of summarize what we've got on the desktop series. We've got the fibers, we've got Onyx. I mentioned we also have nylon white not pictured here, and we've got Precise PLA. And when I look at this materials list, I'm really kind of feeling like I'm not really wanting for any additional material. When I imagine the kind of things that I want to do in manufacturing, I'm generally looking for things like great tensile strength, great compressive strength, great impact resistance, great heat resistance, great chemical resistance, low cost for prototypes, impact resistance. And when I think about all those attributes, this really covers that well. So when I line up those requirements and compare them to what else is out there commercially available today, across these properties, tensile strength, temp resistance, chemical resistance, the impact resistance, the cost effectiveness for prototyping, the surface finish, which I mentioned, Onyx has this really stable print process. I can show you this part here. It almost looks injection molded because I can't see the layer lines on it. So when I kind of add up all these properties, we're really covering the most expansive set of properties with a versatility and an extent to these capabilities that's unmatched across other desktop FFF machines. FFF, for those unfamiliar, stands for fused filament fabrication. You might also be familiar with the term FDM, which is coined, I believe, by Stratasys. That really just means I'm extruding a material from a spool out of a hot nozzle. We have a question here, more of a comment here, just about the pricing. That's a decision-making factor in sort of how people look at this, and specifically when we think about the cost effectiveness on a per part basis. Before we released Precise PLA, a lot of customers told us, "Hey, I love your equipment, but really I'm only sticking with tooling or production parts on my Markforged platform. When I need cost-effective prototypes or concept models or fit checks, that could be accomplished on a lower cost machine." And really, we took a look at that and said, well, our customers really deserve to have this same consistent, high quality experience, even when they're doing the low cost fit checks and concept models. So now what we've done is we've unified that capability so that I can stick with one platform from prototype to concept to tooling to production. So I really don't have to compromise at any stage in the product life cycle here. We got a question here in the chat box. Are any of the current materials approved for FDA use? If not, is there any future plan to supply material for this use case? We don't have anything purpose built for FDA use. I've heard anecdotally of some use cases where customers on their own qualified nylon white for certain applications. Again, that's a material that's available on the Mark II. We've certainly heard that feedback from customers that this would solve a huge problem. So certainly something that we look into. And just by the way, for reference, we announced a new material, I think something to the tune on average. I've been here about 5 years, and in those 5 years, we've released 15 new materials. So call it a 3 material per year cadence. We release new stuff. So always just keep an eye on our website and the news and all that stuff for updates on our latest material list. Again, I appreciate the questions and comments. Keep them coming, and I'll continue to try to answer in real time here. So getting back to the slide here, the main point I'd like to convey is I would contend that you'd be hard pressed to find a more versatile platform in not even just the desktop FFF space, but really in the manufacturing space. Another question here: can I mix Kevlar and carbon fiber in a single part? That's a great question. So I've had the need to do that a handful of times. Sometimes I want to use sort of the durability of Kevlar on the outside of my part for impact resistance, and then I kind of want like a carbon fiber skeleton. So what I will say is you can only load one fiber material at a time. But I've made a bunch of multi-part assemblies where I sort of inlay a part into a secondary part that sort of has the shell. I would definitely recommend, if you have a use case that needs to blend the two, reach out to our technical experts on the application engineering team. I used to be one of those myself, to help you with the implementation for that particular part. See another question here. A question here about including a widget like the one on the screen here. Is there anything in Eiger that can sort of recommend that the right material for you? The way I would address that today is again probably working with our technical experts on the application engineering team. I can definitely share a little bit more information on this call today if we have time at the back end, just about which materials are best for each use case. The long-term answer to that is Eiger is always getting more capabilities, and we can definitely imagine a case where it gets smarter with the recommendations. So we'll file that one away in kind of the suggestion box, let's call it, and I'll think a little harder on that. Question about the technical properties of PLA. I'll pull up a data sheet when we get to the end of this call, just so we can compare and contrast how that lines up with some of our other plastics. But what I will say is for the technical properties here, the thing that Precise PLA does best is cost effectiveness. Across each of these other technical properties, the Onyx is going to be the best material that I'd recommend for any sort of technical application. Just a question here. Oh, I'm actually going to write this down. Looks like the Precise PLA datasheet isn't available on the Eiger support site yet. I'll make sure that's available, but I'll pull it up here today at the end of the call, just so we all can take a look at that together. Cool. So just moving along. So I mentioned sort of different applications, different phases of the product life cycle. I'd like to spend a little bit of time talking about actually like application itself. So just sort of dividing this up by the product life cycle phase, right? So do I need a visual prototype? Do I need a functional prototype? Do I need a tool or fixture? Or am I actually looking at production parts? So I would really recommend Precise PLA anytime you're looking for something that needs a pretty solid appearance and accuracy. I need some colors, or I need low cost. That's going to be the realm of use cases where we would definitely recommend Precise PLA. There's a question here about the temperature that Precise PLA is rated for. I believe we have that heat deflection temperature in that data sheet. I think it's somewhere around 50 Celsius. Another question here about dimensional accuracy. We haven't characterized the accuracy of Precise PLA yet. It's something we're in the process of doing. But what I will say is generally, if you're looking for super precise, super accurate parts, Precise PLA is going to be a great entry point to that. I've been finding that my Onyx parts and my fiberglass and carbon fiber parts generally come out with slightly better accuracy. I know that's not a numerical answer, but just qualitatively, that's what I've observed just printing on my own. Cool. So getting back to this application map here. So I mentioned we do Precise PLA for whenever I need low cost or colored concept models, fit checks, and prototypes. When would I go to Onyx? It's really when I need a great surface finish or if I need an incremental boost in either accuracy or strength. So we see customers using both of those materials for prototyping, depending on what the technical requirements are. In fact, I've also seen people that need great strength in their prototypes. They need to validate a design and actually apply physical loads to it. In which case, we see customers going to Onyx and fiberglass, or even something even sturdier like carbon fiber. Beyond that, let's say we really need some really sort of functional tools. So sometimes I need like a robot gripper or a work holding tool that's going to hold something in a machine vise. And sometimes those things actually need a pretty good boost in strength. In those cases, I would go to Onyx and I would reinforce it with prototyping, or sorry, with fiberglass. Sometimes I need even greater strength. Sometimes I'm machining Inconel and I need to grip it in a 300 psi vice jaw. Those are going to be cases where I'm really going to need that rigidity of carbon fiber, which is about twice as stiff and twice as strong as the fiberglass. From there, we also see a bunch of high temperature use cases. So am I making a weld fixture? Do I need an injection molding tool? Something like that, we would actually recommend HSHT fiberglass, which again is a specialty fiber that's designed specifically for high temperature applications. It also has really great impact resistance to boot. So for things like enclosures or tools that need to have great impact resistance, I would definitely recommend either Onyx reinforced with Kevlar or Onyx reinforced with HSHT fiberglass. Across production, we really see customers using the whole gambit. But generally, we're seeing customers use Onyx with reinforced with some kind of fiber, depending on what the technical requirements look like. We have another question here just about surface roughness. We've never actually characterized an RA value. The reason we haven't done that is because it's so darn geometry dependent and so dependent on some other factors like what materials we're using, what layer height we're printing in. Just by the way, the background is on the desktop series, we can print anywhere from 100 microns to 200 microns in layer height. On the industrial series, we can print anywhere from 50 microns, so about half the layer height of our lowest layer height on the desktop series. And we can actually print all the way up to 250 microns in a mode called turbo print, which is actually depositing a thicker bead. So in practice, turbo print is going to be about twice as fast as a 200 micron print. What I would recommend is if you're really looking carefully at the system and the Markforged platform, I'd recommend you either come find us at a trade show or meet up with one of our value-added resellers, where you can just go observe some of these parts in person. Again, I'll try to showcase this part that I printed this morning. It's actually quite difficult to even see the layer lines that are typical of a 3D printed part. We'll answer that one. Another fun question here: is there a recommended bonding method? Either two-part adhesive chemical welding for each of these materials. I'm not quite as sure for Precise PLA. Let me file that away as something to follow up on. But frankly, just like your typical super glue, cyanoacrylate is a really good start. Specifically, Loctite 401 is a blend of that or a subclass of that actually forms like a really great, super strong chemical bond between two Onyx parts. I think there's a separate one that does really well for there's a separate Loctite that does really well for Onyx to metal parts. I also use there's like a Scotch weld adhesive that works really well for Onyx to metal parts. Precise PLA, and I've done a couple parts that I just use, again, just like your typical cyanoacrylate super glue. So that's sort of my baseline recommendation there, but I'll check with the engineering team to see if they've had better luck with anything else. A question here, just about another process-related question. How do you purge the nozzle and heat break when transitioning from Onyx to PLA on the same printer? So the load utility itself does a pretty good job of just spitting out whatever's left in the print head. We also ship PLA with a Precise PLA with a with a purge rod, or like a purge kit that just you unfasten the Bowden tube that goes into the print head, and then you heat it up to the load temperature, and then you just sort of force out any kind of residual material that's left in there. Thanks for that question. Another question just about our trade show schedule. This one specific to the sort of Southwest region. I actually don't know of anything coming to the Southwest region anytime soon. That's like a big show. I know we have a federal trade show that's that I believe is going to be hosted by InQtel, where we'll be exhibiting with a handful of parts. I'll probably bring my Mark II as well. So that's I think that's coming up in the second week of May. Another question here looks like someone that has a healthy base of experience printing with Onyx. Is Precise PLA as moisture sensitive as Onyx? We find it's not quite as moisture sensitive, but we do find a lot of benefits from keeping it in the dry box. So for that reason, when you use it, if you're familiar with printing with our system, you probably see over my shoulder here, I've got the dry box, which is it's like a Pelican case, totally moisture sealed. I find there's a huge advantage to keeping the Precise PLA in there. So that's our sort of recommended process. Cool. So getting back to the slide here, just the overall takeaway between the last slide that showed that radar chart and this slide that sort of actually maps out these materials different applications. What we really find is we have a really broad range of use cases that you can address with just one printer on one platform. That really brings to you as users a versatility and a set of capabilities that you really can't match with any other FFF style printer. So to give you a practical example here, this is a bracket that I worked on with a customer that actually is it's an academic institution that's competing in Formula SAE, which is a competition where a national competition where they actually develop a race car. So this was this bracket here is a bell crank suspension specifically for that race car, and it's got to be lightweight, it's got to be strong, and it's got to be accurate. So when I first started down this road of designing this thing, I first wanted to check to make sure the thing fits. So going from kind of back to front in the process, I first sort of took the design itself and just made sort of a shape that fit. In the next phase of the process there, I started to kind of whittle away some material to try to make some weight optimizations and also do some design for assembly stuff as well, make it a little easier for the whole thing to come together. In this third iteration here, now I'm really starting to get this thing where it's optimized for weight. I've got all of the different sort of hardware and fitting and other sort of mechanical considerations and design considerations in there. And then I finally end up at my final part, which I've made with Onyx reinforced with continuous carbon fiber. And now that part is fully optimized and ready for production. And the beauty of this is when I want to go from that final version of design that's validated in the Precise PLA to Onyx reinforced with continuous carbon fiber, it's really a matter of a couple of clicks of a button. When customers used to do this in the past, what they would have to do is load the part into a separate type of slicer or printing software, get it all optimized and dialed in with those settings on that slicer. And then when they're ready to move into the production part, they had to bring it to Eiger, which is our slicer. And I'll actually show this process in a moment here, where they'd have to then go set up the part and do it all from scratch. So that's no longer the case. Now I can sort of iterate and design and manage my versions all on one simple, easy to use platform. Separate question here: would Precise PLA be satisfactory for takeout dining utensils? Again, we don't really have anything in the platform that's devoted to food safe. use cases or applications. But again, that's going to be something that we should just kind of keep an eye on as we continue to innovate and deliver new materials. Is there a possibility to export the Eiger model with its infill to do finite element analysis? We don't have that tool today, but what I will say is our software is getting smarter. Like I think I see an update come through on Eiger every week or two. So that's another case where we don't have it today, but it's certainly something we see our customers have a need for. Got a question specific to the metal printers. Not exactly the focus of conversation today, but I think it's relevant in that we have a question here about downtime for alternating materials on the metal printers. Across all of our print systems, they're all just fed by a spool. So the process takes 2 to 3 minutes of just heating up the printer, getting the material flowing through the nozzle, snipping it where we want to cut it off, and then loading up the next spool of material. So whether I'm changing from 17.4 stainless steel to copper on my metal printer, or if I'm switching from Precise PLA to Onyx on my composite printer, that process is a matter of minutes, and it's super simple. Cool. Again, thanks for the questions, and keep them coming. So I'm going to go ahead and switch gears here, and I'm actually going to show in practice a part that I actually had a lot of fun designing. I actually have the part here on my desk. So what is the part for? It's an ergonomic tool. So this is a wrench. It needs to be really stiff, so it needs to resist torques. And holy smokes, I can't even bend that. It needs to be relatively attractive because it's going to be a production part that's actually going to be facing customers. So you can see I've actually sort of labeled this thing with this carbon fiber, and that came out really smooth and slick. And then really maybe the most interesting feature of this part is I've actually pressed in a secondary set of hardware in the form of these little ball detents, which you can see under the surface here. And really what that's for is this socket, which actually this socket itself was printed on our MetalX platform. So what happens is with those ball detents, when I snap this part in, it has this really satisfying kind of like almost production feel to it. Very satisfying, very ergonomic, and sort of has that almost Apple level quality of usage and the feel to it. And this is great here because I see there's another question about what's the price comparison of Precise PLA by comparison with some of our other materials. So Onyx is $189 per 800 cc spool of material. Precise PLA comes in 600 cc spools, and that material is going to go for about $50. So in practice, when you're comparing apples to apples volumetrically, Precise PLA is a little over a third of the price of Onyx. And what I'm going to do is I'm actually going to show you in practice when I was designing this wrench and sort of fine tuning that nice sort of satisfying feel along with how I wanted this handle to feel and how I wanted that text to show up. I did a bunch of iterations of that part. And I was actually conscious about the price of these parts. So for that reason, I wanted to stick in PLA before I moved to the more expensive materials. So let's go ahead and explore that process now. So this is Eiger. If you're not familiar with Eiger, it's our cloud-based slicer and sort of parts management platform. It's super simple to use. It's accessible anywhere. You can access Google Chrome. So all I do to get here is I type in eiger.io and then it takes me here. You can register and create a free account at any point. And you really never have to pay for it unless you're accessing some of our Fleet Eiger capabilities, which are kind of devoted to doing some sort of interesting team management, version control type of processes. So I've got this part set up to print in Precise PLA. In this case, I've selected red material. I can really select any color. And I have it printing at 200 microns, which is kind of like, I would think of that almost as like a draft mode. And And then in this panel here on the left side, what's kind of cool about Eiger is it's always keeping track of how much material I'm using, what the print time is going to be, and what it's going to cost me. So in this case, this is going to cost me $2.30. Not bad for a part that's pretty substantial in volume. I've got some support material in there. This is a cost and print time where I feel comfortable doing a lot of iterations to really go for style points, which really gives me the freedom to kind of ideate and create and really get to that kind of fine tune. A couple of questions here. Which commercial software is your software compatible with? So when I want to bring a part into Eiger, let's just back up into my part library here. So all I do is import what's called an STL file. So STL files are exportable from pretty much any CAD software. So if I say, let's do that bell crank that we looked at before. This is a component of that assembly. So all I do is import the STL and then bring it in. And then let's say I want it to be Precise PLA. So that's all that it takes to go from your CAD software to our Eiger software. So super simple to use, very, very quick and efficient. And again, any CAD platform you use, whether it's Autodesk, whether it's SolidWorks, whether it's PTC, all of those software platforms are going to have the capability to export an STL file. Another question here. When will Precise PLA be available for purchase in Brazil? If I'm not mistaken, that we have partners already in Brazil that have ordered some. We can definitely follow up on the back end and get you in touch with the people that are supplying that in Brazil. Just a question here again about the design of the wrench itself. So what was that part that went in there? So master car. So I ordered this part. This is a spring plunger. It's in specific called a ball detent. So and I did a press fit, which and I believe the one I ordered was metric. I'm gonna try to find the exact one just so you can see what we were working with. And I happen to know the diameter was 6 millimeters, and then the length was that's also 6 millimeters. So it's probably one of these. It was stainless steel, in fact. So I bet I bought this one. So all I did was, you can see it, McMaster, you can just download the part. So I just downloaded the part and then fit this thing to fit the design to support this press fit. So I just sort of designed a cylindrical blind cut in there. And I'll be honest with you, it took me a few iterations to really fine tune the fit that I wanted and get to a point where it's easy to assemble. Not to mention just sort of the sort of design of the cavity where this socket was supposed to go. Just sort of designing that so that it fit perfectly. You can see I kind of got these sort of depressions on that surface of the socket. So just getting that interface to work really nicely took a lot of iterations, and that's really where Precise PLA comes into play. Are there different temperature properties that are important in selecting the color of P-PLA? Or can I just leave the color the same in Eiger software and simply change this full color? To be perfectly candid, right now, I believe the profiles are all the same, but again, I'll mention the team is constantly fine tuning it. And we are noticing like very, very, very minor variances across colors in terms of what prints best. So I wouldn't be surprised if the team released a software update that made the extrusion and temperature profiles more color specific as well. So if you can help it, I would definitely recommend sort of lining up the colors and in software with what you actually got in the printer. But between us, I've been doing a little bit of that myself. So I would say at your own caution, but I would say if you can, I would definitely make sure to keep the colors matched up properly. What does the color choice do in Eiger? The colors, whatever loaded in. That's right. So it will actually check the compatibility. So when you load it in the printer, it will ask you what color spool with Precise PLA you're loading, and then you'll actually want to make sure you're lining up with that in software. So going back to Eiger, and I'm actually going to go back to this wrench part that we had going in red Precise PLA. So I've got my wrench here. And let's go take a look at the internal view just to see sort of how Eiger is going to slice and print this part. So in this view, the purple material is all support material, and then the rest of this body is going to be the actual end part material. So as I sort of slice through this part, and you can think of this almost like an MRI, you can sort of see the inside of this part. We're using this efficient lattice structure to ensure we're sort of making the best balance of part quality, strength, while also keeping the print time and cost down. So this is sort of how it's going to print my part. I'm pretty pleased with this. You can see I've got my sort of depressions here for the ball detents. This is sort of where that socket's going to go. I can sort of check to see if and how it's going to put material in there. I specifically designed those sockets so that I'm not getting a lot of support material inside of this hole. And that's just sort of a design technique I can share a little bit more about if we have time at the end of this. But really, so I'm pleased with the way it's going to print this part. So in practice, when I was designing this component, I ran a bunch of iterations like this. You can see this is Rev 10-B. You can imagine how many different iterations I went through before I got to the final one. It's definitely more than 20. And the beauty of it is it doesn't really matter because, again, we're looking at $2.32 for print cost. So now let's say I've gotten this design to where in Precise PLA, it's working exactly as I want it to. What's the process now of going from Onyx and reinforcing it with continuous carbon fiber? And this is what's really cool about the platform, because again, if I were looking at a different type of process on a different type of platform, I have to go through that whole process of uploading, optimizing, picking orientation. I have to do that all over again. So really, when I did this, all I did was I used this feature here, copy part. This just makes a new version. I'm just going to say dash carbon fiber for this one. So now I've got my copy. I can always go back to my Precise PLA version through this panel here that's managing my versions. And now I'm just going to say, okay, I want this printed in Onyx, and I'd like it to be reinforced with continuous carbon fiber. And I'm going to go ahead and save that. It's going to just take a moment to slice that. Just a question of transitioning from Precise PLA to Onyx. Is the accuracy across the two materials such that when I refine and design in Precise PLA, will that transfer directly to Onyx? To be perfectly honest, I took a couple more iterations when I moved into Onyx from Precise PLA, but it saved me a lot of the heavy lifting with fine tuning some of the fit and features. So in practice, the clearance that I was looking at in Precise PLA was something like 210 microns. When I did it in Onyx, I was actually able to take that down a little bit for a little bit of a firmer fit. And again, that's just because Onyx prints with slightly better accuracy by comparison with Precise PLA. Cool. So I've now sliced this part for Onyx and carbon fiber. Let's take a look at these part details just to see. And remember, it was like something like $2.30 something for the Precise PLA version. I'm now looking at $7.50. So kind of a difference there just right off the bat. I will say mostly this part right now is just because of the default settings with continuous carbon fiber. It's probably mostly Onyx we're looking at. So again, kind of in keeping with this trend of Onyx being about triple the price of a part that's printed with Precise PLA. But again, you're getting better accuracy and surface finish for that. But now let's really start to think about the strength. And some of you may be looking at this part and be thinking, why the heck did he print it in that orientation? Really, the reason I printed it this way is I needed the part to have a lot of mechanical stiffness and strength. So in this plane, it's got to resist bending forces. So what I'm really looking to do is put a bunch of continuous fiber in this sort of plane that's parallel with the build plate. So let's go do that. So let's look at this internal view. And you can see I've got a little smidgen of carbon fiber at the top and the bottom there. That's okay, but what I'm really looking to do is bring continuous fiber into this sort of length of the range. So I'm just going to go ahead and find where the bottom of this feature is. It's really nice with this updated internal view. Now I can now sort of click and drag exactly where I want to put it. And I don't need a whole lot. So I'm going to go maybe 16 layers. And I'll try to balance it so the top and bottom are the same. So I'm just going to say create group. I'm going to use fiber in this group. And just a question here about cost. Yes, so the question here is are we talking about the cost of just making the part itself, like in total, or is this just materials? So this is just materials. Very astute point that you need to consider things like the maintenance cost of the equipment. You need to think about the cost for even the electricity to keep it running. You need to think about the cost of the machine itself, depreciated across a wide range of parts that are printed. So all of those sort of like costs that go into the part are valid. What we find is because our desktop printers are so affordable by contrast with say like a CNC mill, generally the cost of the materials actually dominates the equation. So that's to say materials generally account for more than half the cost of printing a part when you factor in even labor, electricity, other consumables, the hardware itself. But again, for more information about that, we definitely recommend reaching out to our application engineering team. They're experts in talking about total cost of ownership, ROI, all kinds of good stuff like that. Cool, so I've got my continuous fiber layer there. Again, I mentioned I kind of want to balance it. So I'm going to find the top of this feature here again, and then click and drag. And again, I had 16 layers there. So I'm going to go ahead and kind of balance that across the central axis of this thing. There we go. So I've got 16 layers selected. I'm going to do the same thing, the create group. Use fiber. Now, while this is calculating, I'll just mention, you can see this setting here, isotropic fiber. Now that's sort of how conventional continuous fiber works, where I have sort of apply at 0 degrees, I've applied at 45 degrees, I've applied at 90 degrees, and I've applied at 135 degrees. So I've kind of got fiber going in all axes. So what does that mean for us when we look in this 2D view here? And let's just take a section that's printing continuous fiber. I've got some fibers going in that 0 degree direction. I got some going in that 45. I got some going to 90 and then the 135. But when I look at this, I actually don't have fibers sort of connecting this total load path here. So really the fibers that are doing me good here are these continuous strands that are going around the outside. And I can accomplish that exclusively with this concentric fiber ring. So I can do away with that. So that looks good there to me. I might want to boost up the strength a little more by just increasing the walls of fibers. And those strands of fibers in practice really just give me a bunch of strength. So really what I want to do here is make these whole groups concentric fiber with, let's just say 4 walls. Cool. So I've done that there. Now let's do the same thing on this one. Concentric fiber. Or apply. Cool. So now I'm getting to a point where this part is really starting to look like a winner to me. It's going to be super, super strong in that axis where it's going to be subjected to those bending forces. And then I've got it to a point where it's going to print with those features the way I want them to. You can kind of see just kind of that breakdown of continuous fibers, support material. and that Onyx material here. Again, the Onyx is sort of the faded out material. Blue is the continuous fiber. And we've now gotten to a cost of $19.11. And it's going to take 6 hours and 47 minutes to print this part. And again, that was by comparison to, I think it was just about a 3-hour print in Precise PLA, and somewhere around $2.32 in materials. So you can see we've increased the cost of this product, but now it's going to print with the capabilities that are going to go beyond just prototyping, and really sort of suit me in some more sort of mechanically robust applications. Namely, in this case, it's actually going to be able to work as a wrench. It's a part that I can actually use. So that's sort of the end of the sort of visual materials I was going to share. I see there's a couple more questions trickling in here. Just a question: can you print Precise PLA with continuous fiber? So Precise PLA is not going to be compatible with any of the continuous fibers. So if you want to print continuous fiber, you actually are going to need to print that with an Onyx-based material. And why is that? That's really because the continuous fiber that we use only activates with a very specific type of polymer. So that's really what Onyx was purpose-built to do. So it would not be able to work with Precise PLA, unfortunately. What are the minimum width and height for a part printing with continuous fiber? Good question. So we actually have like a really comprehensive design guide on this topic, which we can definitely share as a follow-up. But as a rule of thumb, in terms of like height above the print head, just to get one layer with continuous fiber, I'm going to need to be a little over 1 millimeter in height. It's going to be much more effective if you get it in thicker parts, especially due to like just bending forces. In terms of the thickness of a feature, we're generally looking at features that are above 4 millimeters in thickness. So 1 millimeter height above the print head, 4 millimeters in X and Y. Good question there. Is there a way to export a solid model from Eiger once the layup has been constructed for the purposes of FEA? Are there recommendations or white papers about doing FEA on parts with fills other than solid? Again, that's not something that we have at this point in time. We do have one sort of software integration that I believe it was with MSC. So that's like a really specific type of composites modeling software that we've done some integrations with. So that would be definitely something to check out. Can you only use Precise PLA on the desktop series? So Precise PLA today just prints on the Mark II and the Onyx Pro. The great news there is we do have Precise PLA slated to come live on the industrial series in April. So I'm looking forward to running some Precise PLA on my friend Big Mike over here. Another question. Can you print multicolor parts, changing the spools during the print? I haven't tried that yet. I bet it would work, but it's only going to be sort of like a transition at the layer, so I'm going to see height. What is the just a question about like if the material is going to age or get sort of like degraded mechanical properties. We haven't subjected it to any kind of like environmental testing, but in terms of the shelf life, like just sort of sitting on the shelf, we recommend using it within 18 months of purchase. Cool, we're coming up to the top of the hour here. Again, super appreciate the participation and the questions. I certainly had fun talking to you all about Precise PLA and the desktop series and continuous fiber and all that good stuff. Again, we'll be sending out a recording of this webinar for you all to consume at your leisure. And again, let us know if you have any additional questions and follow-up. Thank you all and have a great rest of your day.